This tutorial will show some of the tools available within ETABS to carry out performance-based design, or PBD. But what is PBD and why would it be used? It is important to understand that PBD is more a philosophy than a prescriptive guide. It allows for designs that follow the intent of design codes without necessarily satisfying the letter of the codes. Building codes often allow an alternative design approach different than that prescribed in the code if it can be shown that performance of the building will be equal to or greater than that of a building design with the prescriptive procedures. And this is where performance-based design comes in, to show that even though the building may not satisfy the letter of the code, its performance will be acceptable. And it should be noted that because the use of performance-based design lies outside the prescriptive code procedures, outside third-party peer review is typically required and prudent. Why might we need to use performance-based design? Well, let's take a look at our building model. This building is a concrete structure framed with concrete core walls, coupling beams, and perimeter columns. It is 30 stories and 302 feet tall. Buildings of this height, for example buildings that exceed 240 feet in height, are often required by code to use a dual system, that is, shear walls plus moment frames to ensure ductility in earthquakes. However, note that this building does not have perimeter beams. There is no perimeter moment frame, and thus is not a dual system. A building developer might desire that the building not have perimeter beams because they adversely impact views and ceiling heights and increase construction costs. By using performance-based design, building designers can take advantage of the alternative methods option in a code and show that relying solely on the core system to carry lateral loads, such as in this building, may still result in a building with appropriate performance. What then is the goal of performance-based design? A simplified statement might be that when the building is subjected to varying levels of hazards, the building performs in such a way that agreed upon acceptance criteria are satisfied. Typically, hazard refers to earthquakes, although it could also mean wind or something else. When dealing with earthquakes, the design process typically involves several different intensities of motion. We might have a service level earthquake, a design basis earthquake, and a maximum considered earthquake. As an example, the service level quake might be an event that has a 50% probability of being exceeded in 30 years, or roughly a 43-year return period. The maximum considered earthquake might have only a 2% probability of being exceeded in 50 years, which would be a return period of approximately 2,475 years, a much rarer occurrence. For a low-level earthquake, we might assume that the building remains essentially elastic. No significant yielding of structural elements will be allowed. This analysis might typically be done using a linear elastic response spectrum analysis. However, for large earthquake, such as the MCE, it can be assumed that there will be significant nonlinear behavior. Certain structural elements will yield, but will maintain adequate ductility to such an extent that the building will not lose gravity load carrying capacity or experience excessive drift or instability issues. The nonlinear elements are classified as deformation controlled or ductile, while other elements in the building that are to remain in the linear elastic range are force controlled or non-ductile. But when components yield, how do we determine whether the behavior is acceptable? We need acceptance criteria that shows that the design satisfies the performance objectives. Acceptance criteria might include strain and deformation limits, drift limits, demand capacity ratios, along with strength calculations. Documents like ASCE 41, can help by providing different levels of acceptance criteria for different components. For instance, when performing a nonlinear time history analysis, acceptance criteria for beams might be provided in terms of rotation at immediate occupancy, life safety, and collapse prevention levels. For a large MCE type event, nonlinear rotation should be below the collapse prevention threshold to be acceptable. In summary, a performance-based design might take the following steps. 1. Perform an initial analysis and design to size members and determine reinforcing. 2. Identify components that should be detailed for nonlinear behavior, the so-called deformation-controlled components. 3. Perform an analysis using a lower-level earthquake, like a SLE, to make sure that the building remains primarily elastic. Elastic analyses might be done using expected effective stiffnesses. 4. Subject the building to a suite of larger earthquakes, MCEs, using nonlinear time history analysis to determine post-yield behavior of components. Material properties used should be based on expected strengths. And 5. Compare the results to the appropriate acceptance criteria. Now let's return to our model. In this building, the core is the lateral load resisting system, and the core walls are governed by flexure rather than shear. Again, there are no perimeter beams or moment frames. We have already performed the initial design and sized our members. Next, we want to identify the acceptable types of nonlinear behavior. For our tall building, we would like to see flexural yielding in both the core shear walls and coupling beams. These are the deformation-controlled components. Flexural yielding of the slabs at the columns might also be a concern with the accompanying issue of punching shear failure, but in this analysis, we will assume linear elastic behavior for both the slabs and columns. They are to be force-controlled components. It is important to identify the zones of inelastic behavior early on to ensure that the models capture the appropriate response and that the design provides the appropriate ductility. And because ETABS offers a range of sophisticated nonlinear modeling tools, including fiber and moment rotation hinges, it is ideal for executing performance-based design. Now we will assign the nonlinear hinges to the walls and coupling beams. Nonlinear analysis can be computationally intensive, so it is good practice to assign nonlinear hinges sparingly, only where there is a good chance that nonlinear behavior will occur. In this case, we are going to assume that nonlinear behavior of the walls will be limited to the first 10 stories. So we select the first 10 stories of walls. There should be a total of 60 shells selected, as there are 6 wall segments per story. Next, we go to the Assign Shell Wall Hinge command. As we have not previously defined any hinge properties, the only hinge available is the auto hinge, which is a fiber hinge. We could define a moment curvature hinge by going to the Define menu, and selecting the interacting PM3 option. Here we can define the shape of the backbone curve, as well as the immediate occupancy, life safety, and collapse prevention levels. However, we are going to go back to the Auto Assign option and use the auto fiber hinges for these walls. Fiber hinges are often a good choice for nonlinear wall behavior. As a note, shear behavior is usually not coupled with bending, and it is desirable to maintain shear demands below shear capacities, that is, to promote ductile flexural yielding over brittle shear fracture. Using the previous selection, we go to the Assign Shell Reinforcement for Wall Hinge command. Here we specify the reinforcing to be used in the hinge formulation. It can be current design, uniform rebar ratios, or we can specify the actual layout. For this study, we'll use the uniform ratio option. We can see the properties of the hinges just assigned by going to the Define Section Properties Wall Nonlinear Hinges command and checking the Show Generated Properties option. This denotes that the hinges shown were generated by the program and not input directly by the user. Selecting a hinge and clicking the Modify Show button, we can see the hinge fiber layout. Including the area, the location, and the material. Note that gray denotes concrete and blue steel. The fiber selected blinks on the plan diagram. The actual nonlinear behavior of the fibers is determined by the material properties. If we go to the Define Materials command and select the 8,000 psi concrete used in the core walls, clicking the Nonlinear Material Data button provides the various nonlinear parameters. If we click the Show Stress Strain Plot button, we again can see the backbone curve. Note that the ultimate stress value is higher than 8,000 psi, as this represents the expected material strength. We can similarly review the nonlinear properties for the steel rebar. Included is the type of hysteresis behavior to use, and for the rebar, we will use kinematic. Next, we select all of the coupling beams. There should be a total of 60, 2 at each story. Unlike the walls, we are going to assign hinges at every level. We think it is more likely that the coupling beams will yield farther up the building than the walls. Again, we could explicitly define a hinge using the Define command. But as done with the walls, we will use the Assign menu to generate an auto hinge option. We start by adding a hinge at relative distance 0. This is at one end of the coupling beam. Our hinge will be a type as defined in ASCE 41-13, and we will use concrete beams flexure. The hinge will be for the M3 moment, and we will select a combo that has gravity and earthquake loads for the shear value, although we could specify a value directly. We will select the transverse reinforcing is conforming option and use a reinforcing ratio from the current design. Next, we will specify the same hinge at the other end of the beam. Again, we can see the properties of the hinges just assigned by going to the Define Section Properties Frame Nonlinear Hinges command. Here we select a beam hinge, and these start with B. Note that it is deformation controlled, and this form shows us the backbone curve, the hysteresis type, and the acceptance criteria. If we wanted to modify this hinge, we simply click the Convert Auto to User Prop button. And the options are no longer grayed out. For instance, we could change the hysteresis type. Hysteresis types, which might include both strength and stiffness degradation, should be carefully reviewed as they can have significant impact on nonlinear energy dissipation and overall model behavior. Something other than isotropic might be a better choice here, but we will not edit the hinge at this time. A right click on a coupling beam shows that two hinges have been assigned to the beam, one at each end. Also note that an auto divide of 0.02 is shown under the hinge overwrites. This means that the hinge has an assigned relative length of 0.02. Having an explicit length assigned to the hinge can result in a more efficient nonlinear solution. Now we will review our earthquake loading. Under time history functions, we have a total of 4 earthquakes that comprise 2 orthogonal pairs. Typically, performance-based design analyses are done using orthogonal pairs of earthquakes, and although we are using only 2 pairs, most of the time PBD studies will require that many different pairs of earthquakes be run, and it is not uncommon to run 7 or more pairs in order to ensure that a significant range of building response is captured. The first of our pairs is LACC in 2 different directions. These were recorded earthquakes and will be scaled to approximately 0.8 G to represent a MCE earthquake. The second pair of earthquakes are synthetic earthquakes generated by ETABS. These earthquakes have a relatively low acceleration, less than 0.2 G, but the motion is long in period. They were synthesized from a response spectrum recorded from an earthquake in Nepal, which had its peak response at around a period of 4 seconds, much longer than most earthquake records. We are using this record because of concerns that our building, which has a fundamental period of around 3 seconds, may be substantially excited by this long period motion, especially as yielding occurs. Now let's review our load cases. Our load cases consist of a dead load, which includes self-weight, a live load, a superimposed dead load, a cladding load applied around the perimeter of the building, 2 response spectrum analyses that could be used for lower level elastic analysis, and then 3 load cases for doing the nonlinear analyses. All 3 of the nonlinear time history analysis cases use fast nonlinear analysis, or FNA. ETABS allows both direct integration and FNA to be used, and we have chosen FNA here as it is often faster. The first of the FNA cases applies the gravity loads. Because we are doing this as a time history analysis, we use a ramp function with a high modal damping. We apply the dead, superimposed dead, cladding, and live loads, all with a factor of 1, except for the live load where we use only 25% of the load. F&A typically uses Ritz vectors. The second F&A case applies the LACC time histories. In this case, we start from the end of the gravity load case and apply the pair of earthquakes in two orthogonal directions. We scale by 3 to get the appropriate peak acceleration. For this case, we will use 2.5% modal damping. It is often recommended in PBD analyses to use a smaller amount of damping than might traditionally be suggested in codes such as 5%. The last F&A case is similar to the previous, but uses the long period earthquakes in the two orthogonal directions. A check of our modal case specifically the Ritz case shows that we are using P delta based on our gravity loads. It is important to use P delta as it is critical in properly determining stability behavior. The loads applied in calculating the necessary Ritz vectors are all the gravity loads, ground acceleration in the two orthogonal directions, and all of the links. We have requested a total of 306 Ritz modes to capture the building response. The last thing we will check before running the nonlinear analysis is the setting for the nonlinear hinges. If we wish to use F&A, which we are using, the hinges need to be modeled as separate link elements. If we were running direct integration, the hinges could be modeled within the elements. And the damping specified here is for direct integration and not F&A. If doing direct integration, tangent stiffness can be more realistic and less likely to overdamp. We are now ready to run the analysis. A check of load cases set to run shows that we have Ritz, dead, live, superimposed dead, cladding, and our 3 F&A cases. We will not run the linear elastic response spectrum cases, as we are only interested in the large earthquake maximum considered earthquake response at this time. With the analysis complete, let's start by taking a look at the behavior of some hinges, our so-called deformation-controlled elements. Remember that we have hinges in the first 10 stories of the walls and in all of the coupling beams in the core. To view the force deformation hysteresis plots, we go to the Display Hinge Results command. We select our first earthquake pair for the load case, and we see the moment rotation plot for a coupling beam at the first story. We will change the line thickness and color of the plot so that we can see the indicator better. And we will also thicken the backbone curve. As we scroll along the curve, note how the color of the indicator changes to indicate the status of the hinge. In fact, this hinge exceeds the defined collapse prevention level relatively early in the earthquake. The 3 hinge status levels, immediate occupancy, life safety, and collapse prevention, are shown on the backbone curve. And because the indicator is shown in light green, we know the hinge is at or past collapse prevention. Thus, this beam may require a redesign. Next, let's look at a coupling beam a bit farther up in the model, let's say at story 10. Here, the status of the hinge is somewhere between immediate occupancy and life safety, a more appropriate level of response. If we go all the way to the top of the building, story 30, the response is linear elastic, and the hinge does not even reach the immediate occupancy level. Now we will take a look at the response of the wall hinges, switching back to story 1, where we might expect the wall behavior to be the most extreme, and selecting W2, one of the long walls, we see the plot for the M3 moment. Note the magnitude of the rotation. We can also see the plot for axial force by switching the hinge degree of freedom to P. Up until this point, all of our results have been for our first pair of earthquakes. We will now take a look at the same wall subjected to our second pair of earthquakes. Remember that the second pair had a substantially lower peak ground acceleration than the first pair, but a much longer dominant period, which we thought might fall closer to the fundamental period of the building. And indeed, we see the magnitude of the response is much larger for this pair of earthquakes. This is the very reason why, when doing a PBD analysis, it is important to subject the building to a wide range of earthquake pairs. In addition to the plots of the hinge response, we can also generate tables of the hinge states. Highlighting a beam hinge, we see that not only is the moment shown, but also the rotation, the hinge state, and the hinge status. For the wall fiber hinges, the table shows us the actual strains and status of the individual fibers. Here we see the results for fiber 17, which is a steel fiber, and the strain, state, and status are all reported. Remember that the acceptance criteria for the fibers was set in the material definitions. One of the other responses that are closely reviewed in performance-based design are the story drifts. The display story response plots command allows us to display different story responses, including diaphragm drifts. We select our first earthquake pair, and a type of max. Here we see that the maximum drift is about 2%. But when we switch to the longer period time history, the drift jumps up to almost 3.5%, significantly larger. Performance-based design might set a maximum limit for each pair of earthquakes, as well as a limit for the mean values of all the earthquake pairs. In addition to looking at the behavior of the deformation-controlled elements, the forces in the force-controlled elements, such as the columns in this model, should also be reviewed to ensure that they are not undergoing significant nonlinear behavior. For a maximum considered earthquake analysis, the critical action in the columns might be limited to the traditional nominal value times some multiplier, for example 1.5, based on the fact that the expected strength is higher than the nominal value. Other force-controlled elements that should be checked in this model would be the core walls for shear demand-capacity ratios. Remember that the hinges are for the ductile moment rotation behavior. This concludes this tutorial on using ETABS to carry out a performance-based design.